Precalculus Online begins now. Let's take a look at the activity concerning cartography. Example number 12. Find the distance from Glasgow, Montana to Albuquerque, New Mexico. Given that one is directly north of the other, the radius of the Earth is 3,960 miles. All right, well, let's put in our cities here. So Albuquerque is about right here. Let's see if that shows up here. Here we go. Here we go. And let's just say that Glasgow, Montana is about right here. Now, the problem says that they are directly north of each other, which means they lie on the same line of longitude. And let's put in the equator. Equator is probably about right here. Goes through Ecuador. That's why it's called the equator. That's why it's called Ecuador, actually. All right, there we go. All right, now, the measurement for these latitudes, here are the latitudes, is given right down here. So the idea is the following. The longitude line is basically a circle that goes around the Earth through the poles and through the equator, etc. And so if I draw now and I put in the center of the Earth, so this dot right here represents the center of the Earth, inside the core of the Earth, let's just say, and then I can project out this way. So I'm going to say here is 0 degrees, going from the center of the Earth to the equator on our particular line of longitude. And then I can measure up to Albuquerque, and this angle is the latitude for Albuquerque. That angle is 35 degrees, 5 minutes. And then I can also, let's go with purple, measure up to Glasgow, Montana. And this angle from 0 up to Glasgow is the latitude for Glasgow. So that's 48 degrees, 9 minutes. And the question asks, what is the distance from Glasgow to Albuquerque? And that's this length right here. It's an arc length. And so our strategy here is to take the sphere that is the Earth and cut it so that we now are just basically playing with a circle, figure out the angles, and do arc length. So let's call this angle theta. And this is the angle theta that we want to compute. So theta is equal to the latitude at Glasgow, which is 48 degrees, 9 minutes, minus the latitude at Albuquerque, 35 degrees, 5 minutes. That is 13 degrees, 4 minutes. Now, in order to do our computation with our formula, which is S is equal to R theta, I need to convert theta into radians. So let's do that down here. So we have 13 degrees, 4 minutes. First, I'm going to convert this into decimal degrees. If you just type in 13 degrees, 4 minutes into your calculator, it will, and press enter, it will return the answer in decimal degrees. So you can do that if you'd like. If you don't have a calculator that'll do that, here's the method that you go by. You say 13 degrees plus 4 minutes, and then the conversion factor from minutes to degrees is 1 degree over 60 minutes. And this is 13.07 degrees. Now I need to take this, decimal degrees, and I need to convert that into radians. Remember that your formula S equals R theta only works in radians. The conversion factor from degrees to radians is pi radians over 180 degrees. This is 0.228 radians. And now we're going to use arc length. So S is equal to R theta. R is 3,960 miles. My angle is 0.228 radians. And so the distance is 903.10 miles. Activity number 2 involves linear speed of an object traveling in a circular motion. So basically, if you have something, let's draw a circle here. If you have an object that is on the circle and traveling around the circle, I have to draw it sort of outside the circle so that you can see it. Then we want to develop the formulas that we use in order to look at this sort of situation. So to think about this, first let's start with average speed of a linear type object. So average speed would be r for rate, and that's distance divided by time. That just comes from the equation distance is equal to rate times time. I've just solved for the rate. Now, if we are on the circle, though, then the distance that's actually being traveled is an arc length. So I'm going to use S for arc length again. And so let's change this now to V for velocity is equal to S for arc length divided by time. So my D is now become an S. No big deal. Now let's bring in angular speed. And angular speed is omega, Greek letter omega. It looks a little bit like a W, but curvy on the ends there, curly at least. And that is going to be theta divided by time. So theta is the change in the angle. And then, of course, we're dividing by time. And then what would the units of this be? Well, an angle change needs to be in radians. And our time can be whatever, but we'll say seconds for now. Just as an example. It could be radians per minute, radians per hour, whatever it is. Now, let's put these two equations together. So I'm going to start with V is equal to S over T. But we know that arc length is actually R times theta. That's just our arc length formula that we've been using all section. And then I'm going to regroup this so that it's R times theta over T. So I just regrouped the theta and the T together. But what is theta over T? Well, that's our new friend, omega. And so there it is. V is equal to R omega. And that is the formula for linear speed of an object that's traveling in a circular motion. Now let's break it down just a little bit more. Why is it linear speed? Well, angular speed has to do with how the angles are changing, right? That's angular speed. Linear speed has to deal with distance, and so we needed to bring in the arc length measurement and then sort of relate it to both of those. What would be the appropriate units here? Well, radius is going to be measured in some sort of linear unit, let's say feet, and omega is measured in, let's say, radians per second. But what should V be measured in? Well, V is speed, and so it should actually just be feet per second. So here again, it's one of those situations where the radian measurement just sort of vanishes because it's more of an indication that we are in the right measurement system in order to do these calculations without having to compensate for the pi's and the circumference and things like that. Let's take a look at example number 14. A child is riding on the edge of a merry-go-round of radius 4 feet. The merry-go-round makes one revolution every 3 seconds. Find the linear speed of the child. All right. So first, let's find omega, our angular speed. And we know that the merry-go-round makes one revolution every 3 seconds. I need to turn revolutions into radians. So the conversion between radians and revolutions is that there's 2 pi radians per revolution. And this gives me 2 pi over 3 radians per second. Next, I'm going to use my equation. Velocity is equal to radius times angular speed. The radius of the merry-go-round is 4 feet. The angular velocity is 2 pi over 3 radians per second, and that is 8 pi over 3 feet per second, or in decimals, 8.38 feet per second. Let's look at example number 15. The Earth spins around its axis of rotation. San Marcos is about 30 degrees north latitude, and thus the distance from San Marcos to the axis of rotation is about 3,434 miles. Find the linear speed of a person in San Marcos as the Earth rotates. And then, is a person in Austin moving faster or slower than a person in San Marcos? All right. So let's draw the Earth. So here's the axis of rotation. And see if I can get a good Earth going here. Yeah, not bad. Okay, there's the Earth. And let's go ahead and draw in the equator, like so. And then I'm going to draw in the line of latitude for San Marcos. And this is 30 degrees. So let's say that here's our person right here. Yay. And this is 30 degrees. All right. Now, the question is, how fast is the person moving? Mark the equator. The equator is 0 degrees latitude. All right, so how fast are they moving? So V is equal to R omega. let's figure out omega. Omega is the angular speed of the Earth. We know that the Earth makes one revolution every 24 hours. I'm going to change this into radians. So that would be 2 pi radians divided by 1 revolution. The 2's cancel with the 24, and that's 12. So this is pi over 12 radians per hour. So that is the angular velocity of the Earth. The Earth is moving at pi over 12 radians per hour. Incidentally, in case you're wondering, that's 15 degrees. So there's 24 hours in a day. One rotation is 360 degrees. So that's 15 degrees an hour, which also explains why there's approximately 15 degrees between time zones. So if you want to know more about that, look that up. All right. Now, the radius here, now this might have been a little bit confusing. We know that the radius of the Earth is 3,960 miles, but the radius that we're actually looking at is this radius right here, from the axis of rotation straight over to San Marcos. So remember that this is sort of a circle right here. This is the back side of the circle, like that. And so this radius right here is the one that we need because the Earth is spinning around its axis. And that's why, and I computed that for us earlier. You will figure out how to compute that later on in this course if you don't know already. All right, so we'll go with 3,434 miles times omega pi over 12 radians per hour, and that is 899.02 miles per hour. And the second question was, is a person in Austin moving faster or slower than a person in San Marcos? Explain. I'll go ahead and let you answer that in the chat, in the comments of the video, and you can share your ideas with other people. All right, that's it for now. Thanks for watching, and we'll talk to you soon.